to keep this brief. So I'm very grateful for all the presenters. We have a full program today, hopefully. So my name is Mike Sperber. I was the program chair for this farm, but most of the work was actually done by my collaborators. And I guess very few other presenters know me. And so David Janon is the general chair this year, got everything started and organized. Mark Santalucito did publicity. Renning Bell organized the performance evening. I'll have something to say about that in about 30 seconds. And here's my program committee. I think a few of you will have been in touch with some of them. And they've been, despite the fact that this is about art, they have been very well organized. And so it was just a pleasure to work with these people. Just like to note that. And I've organized quite a few workshops in my time, and this was one of the better organized ones. And not to me, certainly. I'm sure your attention has already been drawn to the performance evening tonight. So it's a Beverly Hills live house. So despite the fact that it's called Beverly Hills, it's here in Japan. You can walk there. You don't have to take a plane. And it's been completely organized by Renning Bell, who's also going to be performing. And as you can see, there's quite an impressive lineup of acts. Tonight, some of those people are here, some of those people are not in here. What's important is this is an event that's open to the general public. So, doors open at 7 p.m. The concert then, is actually going to end at 9:30, so we really need to start on time. And it's essentially free, but you need to get a drink ticket for 500 yen, which I think is quite reasonable. Now, it's quite easy to walk there. Unfortunately, the map is a little bit misleading, but if you walk down the main street towards Kintetsu Station, Kintetsu Station is right there. So if you see it, it's right on the other side of the street from Kintetsu Station. Just before it, you turn right, and you walk until you see the Beverly Hills Lighthouse. And it says that in Roman letters. So don't or find a group that will. I'm sure there's going to be at least one group that's going to walk there from here. Remember, this is a workshop. Our esteemed colleagues at ICFP, they like to poke holes in presentations. So today we're really here to make the best of what we have and to be encouraging to each other. So I invite you to do that, and so that we can have a lively and good event. Thank you all. Enjoy. And we're going to start with Jay McCarthy, who's going to give the first presentation. Thank you.
All right. Thank you so much. So today I'll be talking about my system for doing synthesis for 8-bit music. So the music is all based on the NES Entertainment System, the Nintendo Entertainment System, but we're in Japan, so it's really the family computer. Now, the family computer had a really simple 8-bit synthesizer in it. It had this chip called the RP2A03. If you look really close, that says 7A. I could only find a picture of the European version. So the European version ran at a slightly different clock rate. So actually all the music that people in Europe heard was different, because one of the things that we'll see is that the music was inherently related to the clock rate of the chip. So my system is a cycle-accurate simulator for the music part of this chip. Now let me walk through a little bit of some of the ways that it works, and sort of we'll talk about the structure of what we'll talk about. By the way, we know a lot about this chip because a lot of people care a lot about it. So this, for instance, is a gate level emulator for it that people have made that you can use to debug your own emulators and that sort of thing. So there's a huge amount of information about this really old chip from the 80s. Now, what I'll be talking about is first how I do a cycle-accurate synthesis of the waveforms that the chip could produce. So let me just tell you what that sounds like. So that right there is just a very simple wave that it can produce. And then from there, I have a a DSL for describing instruments that you can use to create notes. And so once you have, so you can just sort of control the way that you create the waves to get actual notes. And then from there, I have a basic implementation of music theory that allows me to do stuff like scales and chords. And then finally, probably the most interesting part, is a synthesizer for, an automated composing algorithm for generating interesting music. And that's probably the most interesting part, but it turns out that it's hard to say a lot about it, so that's probably like a quarter of the talk talking about this. But let me just give you an example of what we're building towards. So that's just an example song. And one of the things that is kind of cool about my system, Bithoven, is that it actually is a mapping of natural numbers to songs. So for instance, that song that we just listened to is this number that you see at the bottom of the screen. And every time I hit the play button, it's going to pick a different number and play that song. So let me just do it again. So it's slightly different. So what I'm going to do is I'm going to walk through each one of these pieces and sort of talk about how we build it up. So the first thing is synthesis. So now with synthesis, the chip could only make 4 different kinds of sounds. Actually, it could only make 3 different kinds of sounds, but it could only make 4 sounds at a time. So it had 2 pulse channels, which is basically just a generalization of a square wave. So this right here is one pulse wave, and this is another. The pulse waves that it could only generate 3 different kinds of pulse waves that were basically different in the width of the signal. So this one is thin and this one is wide. There's also a triangle wave and there's a noise channel. So, whoops. So we're going to use the pulse wave for, which sounds like this. Whoops. Click the wrong thing. Why isn't it? Uh-oh. Running the program inside of the slideshow may not have been the best idea. All right. Okay. So the 2 pulse waves just sound slightly different, and these are just the pictures of the waveform. So everything is about generating these and turning them into the notes that we care about. The noise channel, by the way, is just a very basic random number generator. It's like an 11-bit linear shift, linear feedback shift register. But let's look closely at how we do the pulse waves. So this right here is the racket code, the entire racket code for synthesizing the pulse wave. So let me just sort of walk through it one thing at a time. So there's these 4 different duty cycles, which is basically the width of the wave. And I have these series of functions for each one of the waveforms that is set up in the following way. You have the function, and it has the parameters that the music can control. So it can control the width, it can control the period, which is basically inside of the chip there's a little counter, and whenever it decreases down to 0, it generates a signal. And so that's a form that you can kind of think of that as the frequency, but it's not actually the frequency. And then the volume. And then there's just a state which we sort of thread through. So there's the input state, and then it comes out on the end as the output state, along with the output volume. And the point of this code is that it's very straightforward to emulate these things, because we just calculate what the frequency should be based on the period of the chip, and then figure out what the width of the duty cycle is, and then just sort of step forward in the cycle. And if we are within the duty cycle limit, then we output the volume. Otherwise, we don't do anything. So the thing that's kind of neat about this is that because this is such an old chip, like the DSP signal for it is really simple. And so that makes it so that the functional form of it is really simple too. And we can make it cycle accurate by just controlling this function right here, this period to frequency function. And there's just a whole bunch of numbers that you need to look up to know exactly what that would be. And so the thing that's neat about this is that this allows us to get precisely the same sound forms that the actual NES would generate. And so I verified this against that, that gate level synthesizer that I showed before. Now, essentially what happens then is that every single every single frame of audio, the music can just control these parameters right here, the various ends, periods, and volumes. And there's a very, very small state space for every single frame, and so we represent this in these simple structures. So there's one for the pulse wave, the triangle, the noise. There's this other thing called the DMC, which I don't actually use. You just have 2 pulse waves. So there's nothing really mind-boggling about how this works. It's a very natural way that you would encode the state of a of a time-varying process. And let me zoom into like how we actually synthesize from this, imagining that there's only the pulse wave. So what I do is I discretize the continuous signal into 735 samples every 60th of a second, which basically is just a control to make it efficient. It really could be anything. In this choice really makes it so that there's certain music that I can't generate because I can't generate changes that are smaller than that, even though the real chip could have done those. So one of the things I'll sort of talk as I get to the actual music is all the various ways that I can't generate any song. I'm generating certain categories of songs that are representative of Nintendo music. And so again, this is the entire synthesizer for something that only does pulse, and basically the real one just has 4 more lines for the other pulse wave, the triangle, the noise, and then another 4 more lines down here to gather those together. And this right here is the only set bang in the whole program where you assemble the byte buffer of the audio that you're going to send out and then send it out to the channel, which is really nice. So now that synthesizer combines all those 4 waves together, and we get horrible sounding things like this, which is just all of them simultaneously. So what we need to do is we need to take those basic forms and control the parameters to make it sound nice. So from there, I build this little FRP language for describing instruments, which is just the shape and sequence of note parameters. So the way that this works is I have this little thing called iPulse, which is a pulse instrument. And I basically have a little structure for describing what the DSL term is for controlling the duty, the period, and the volume, which are the 3 parameters that you have control over. And it really is just a basic implementation of an FRP system. So, just like Yampa or something like that, where we know how many frames of audio we're going to generate, and so we just evaluate these little programs over the length of that little cycle. Now, the thing that's neat about this is that we can then encapsulate different shapes of pulse waves. So what we're going to hear right now are a whole bunch of middle C notes played with various different FRP programs. So this one is just a constant period, a constant volume, and then the second duty. And so the only thing that's different about that and the raw sound is that we that we know how long to play something for, and we can switch the sound. But what's interesting is that we can now build new kinds of instruments. So for this one, what we're going to do is we're going to simulate tremolo by modulating the volume over the length of the note. So it's right here, we're modulating the volume. And so this is the way that we write down our FRP programs. And then we can also do something like a linear decrease of the sound. So it starts off high at 7 and then decreases down to 0. Now, this then builds up to a really useful FRP combinator, which is ADSR. So ADSR stands for attack, decay, sustain, and release. So the first mechanical synthesizers and electric synthesizers like the Moog were based on this model. And so we can sort of look up in a book all sorts of different ADSR templates for different sounds. So this one I call Plucky. It sounds kind of like a little bit like a little bit like a string instrument. And so what it does is it takes the length of a note and breaks up into 4 components, each with their own little FRP program. So it's constant for for a fourth of the signal, and then a linear decrease from 14 to 7, and then constant 7, then a linear decrease from 7 to 0. And so that small change makes a big difference. And this one, any extra frames that we have go into that release phrase, which is this last one, the decay, which is why the signal is basically gone at the end. We can change this just a little bit to make it so that it is any extra frames that we have go to sustain, and it's going to sound really different. So this sounds more like someone holding down a key on the piano. Now, we follow the same pattern for all the other instruments. Yeah?
Just a small question, maybe I misunderstood the constant thing, but isn't an ADSR usually, would you go to linear first from 0 to your maximum value?
Yeah. So traditionally, so ADSR stands for attack, where you increase, decay, where you decrease, sustain, where you keep it the same, and then release, where you decrease. But really, the way that I implement it is just that you can have just 4 different signal combinators at each one of those 4 spots. And so yeah, a traditional one would have always linear, linear, constant linear. But I sort of get a lot of value from doing other things. And that's kind of what's interesting, because you can then change what the various timbres are. And the way that the original like Moog synthesizers worked is they were hard-coded. I mean, they were like physically built. They could only do linear increase, linear decrease, sustain, and linear decrease. Yeah. Now, we do the same thing with all the other instruments, and probably the most interesting thing is that it really doesn't take that much code to express really differently sounding things. So right here are the three instruments that control the noise channel, which is just static, and we control that noise channel to make something that sounds like a drum kit. So let me just play that real fast. And so each one of those crashes is just a different way of handling the static noise. And so on all of these, the parameters are like the period for how fast we're changing and what precise constants we have on the ADSR of the volume of the random sound. And so there's sort of a lot of art and experimentation in figuring out what things sound remotely like a real drum kit. And I don't really have any good theory of that. But so from this base, I then build up a little library of music theory concepts. So stuff like, what exactly are notes? How long are they? What does it mean for there to be a tempo? There's not really any interesting code here, but it's sort of like some basic stuff. The first thing that gets kind of interesting is when I think about scales. So scales are basically notes that sound good together. It's kind of a layman's reading of what a scale is. But scales, when you talk to an actual musician, by the way, I have no musical talent. That's kind of why I'm interested in doing this, because I have no talent. So I'm interested in like, how can I make a computer that appears to have talent for me, given that I have none? So if you talk to a normal person about a scale, they'll talk about, oh, well, that there's particular scales that are particularly that are notes that sound good together. What I do is I take sort of an abstraction of scales, which is that they're sequences of notes which have certain gaps between them, and I call those detached scales. And then I can take those detached scales and fix them to a particular place in the sequence, in sort of the infinite number line of tones, the ones with decreasing octaves and the ones with increasing octaves. And then from those, I can abstract various kinds of scales to generalize gaps between the notes. And once I can do that, then I can talk about an abstracted tone, so a tone that is a certain depth inside of one of these abstract scales. And that's actually the space that the Bithoven composition algorithm uses. It only composes these abstract tones, which are then fixed right before they're played, which makes it so that I can sort of automatically transpose music into different keys and different scales. And that's really valuable because it means that I can use the scale selection to create a kind of sense of emotion in the music, which I'll show later. Then I build a really basic tracker, basically a way to write down sheet music, which is another tiny DSL. And then I use these abstract tones to build chords. Basically, chords are a subset of the scale that if you play them all simultaneously, people think it sounds good. And there's a huge variety of different scales. So every time I hit this play button, it's going to pick a different set of chords to play, so I'm not really sure what it's going to sound like. So that sounds really more full than just playing a single note by itself, and there's a variety of different chords. So I'll play it again, and we'll hear something different. So there's in principle, there's an infinite number of chords that you can play if you move them around on the number line of tones. But what I do is I truncate that basically to the ones that you can play on a piano, because you could have like infinitely high ones or arbitrarily high, that would like sound horrific to us. Okay, so we don't play those chords, even though technically they're chords. All right, now here's kind of the punchline. So in Racket, we built this library called Data Enumerate, which is for describing a data set and then automatically having a bijection between that data set and the natural numbers. And this is really useful for doing things like random testing, because we can just select numbers and we'll know that we can get elements of the input to your function, and we'll know that we'll never get the same number. We'll never get the same input twice. We'll never miss numbers if we go in order, things like that. So Data Enumerate is this encapsulated library for this. So it has a bunch of combinators. So this one is called string E. So we have this function called toNat, where you give it the enumeration and the thing that you want to turn into a natural number, and it tells you what the number is. So we have Bithoven goes to this number. And if we take the number like 42, we can say from nat and see that that goes to the string Q. So by using these combinators, string E, and we have stuff like conz and building vectors and doing, it actually has a monad structure naturally. So there's a bind operation. So anyway, so we can build descriptions of data sets and automatically get bijections between them. So we use this, so I use this to describe a data set for musical compositions that sound decent. And that's what Bithoven is. So I'm going to walk through this. This is the entire code for Bithoven. So I'll start down here. So Bithoven is an enumeration of a vector, which is just a way of having different pieces. And it has a dependent piece and a non-dependent piece. Let me just say something about the non-dependent piece first. I fixed the base notes so that they don't depend on anything else, so that the base notes in all the Bithoven compositions are kind of like are very stable, and they all they don't vary very much. I'm not really sure why this sounds good, but I tried to do it a different way before, and my wife was like, no, that doesn't sound good. So I listened to a whole bunch of the Beatles and looked at their stuff, and I found that they don't really do that much with the bass, especially their early stuff. So I kind of adapted some of the patterns that I saw there. Then there's the dependent piece. So the dependent piece is this little do right here, where we first select a time signature, and so that it can I only generate 4/4 and 3/4 music. In principle, you could do any of them, but those are the only ones that I generate. Then what I do is I select among many different accent patterns. So basically, like what notes will be emphasized, whether it's the first beat of a measure or the middle beats or the off beats, if I want to do something like that. So this is just to create some styling in the music. These accent patterns are going to have an influence on when we're allowed to do things like chord changes, because we're going to program it so that Bithoven will only ever do a chord change on an accent pattern. The thing that's important about this is when I leave this out, it makes it so that the algorithm doesn't sound like music. Like you can't feel the structure in it because it's just changing chords willy-nilly. So even a small set of accent patterns seems to make a big difference. Then what I do is I select among a database of musical forms and chord progressions. Now the musical forms are things like A, B, B, A. So that's like a musical form, or A, B, C, B, A. And so this form enumeration is just a database of forms that provides kind of the superstructure for the song, which is the repetition that you can detect as you're listening to it. The next thing that I do is I select from a database of chord progressions, which chord progressions are basically rules that say something like play the first chord, then the 8th chord, then the 3rd chord. And if you play in that sequence, then people think that it sounds good. And these come from a huge database of music from the Common Practice period, which is basically like 400 years ago to 300 years ago, maybe. And so there's a large number of chord progressions that are in classical music. So I just sort of mine those and then put them into the program. There's something like 25 of them. Yeah?
See the question, why would you do this course and then extracting it immediately?
It's something that's important about data enumerate is that when you form structures, it will fairly explore them, but when you don't form a structure, then it will bias towards the first thing. So by putting this cons here, I equally explore forms and chord progressions, but if I instead just had a sequence in binding, then it would kind of explore all the forms and then explore all the chord progressions. And that's going to change the order of the songs, and it's going to make it so that if you like add one and then look at the next song, then you're going to get something that's in the same form. And so you're not going to have as much variation. One of the things that I do, one of the things I use this for is generating music for retro video games. And in those games, I kind of do it live, where every level I basically randomly decide to go somewhere within 10% of the song that you're at right now. And so by having as much fairness as possible, it makes it so that there's a good amount of variability. Yeah, so it does, yeah, you're right, it does look kind of dumb. This squiggly arrow is basically like a list map. So it's sort of, because we're in Racket, there's not really any type system, so this is just, this do notation is just for helping you with using the monad. And so what this is going to do is this form part length thing is a whole list of values, and so we're going to return a list of things here. So essentially what we do is inside of the form there's various parts. So there's like A, B, and C. So we're going to generate a different set of notes for every single part. And that's really where the interesting stuff comes in, which is we go up here. So essentially what happens right here is that we're going to take the number of chords in the chord progression and multiply it by the number of measures that we have available. So if we have chosen to play 4 measures, and there are 3 chords, then what we have to do is we have to divide all the notes in that according to all the 3 possible chords. And essentially how Bithoven music is going to work is that it's always going to play it's always going to play the same number of measures and the chords in the same order, but it's just going to say allocate 50% of the notes to the first chord and then half of the remaining ones to each of the other 2 chords. And then maybe it'll do that in part A, but then in part B, it'll sort of prefer the 3rd chord. And so what we do is we enumerate all the possibilities of that, guaranteeing that every chord gets played at least once. And that's really the only rule that gets followed. And so that's this chord pulses thing right here. And then what we do is we select among various rhythms for a single measure. And basically how this works is that it basically divides up the measure, and then among the available notes in the chord, it just arranges them in one of the combinatorial options of choosing something for harmony, melody, and bass. It just sort of lays out what all the different options are. And because of the fairness, they're kind of spread out in a nice way so that they don't all sound always the same. And so that right there is the entire music composition. And then what we do is we orchestrate that by attaching it, by making decisions about like what instrument will be played, what scale to play on. And so this is just another enumeration for that. And so it does stuff like it chooses what kind of scale to use. And so this might be like a diatonic major or a natural minor. And then it says, am I going to play a C scale or an E scale or a G scale? And then we're going to select a tempo, the various kinds of instruments that we're going to use, and then what drums will be used for each part. And then this right here is just a term that is essentially the musicality term, where it's going to arbitrarily change some of the notes from what Bithoven said it would do, and it's just going to arbitrarily change those, maybe turning them off, maybe breaking outside of the chord into something else that's in the scale. And it has this parameter for not doing this too much. And so I don't really have a good explanation for why this works, but it seems to sound good. I wish I could say more about it. So the whole system is about 2,200 lines, and you can see the line breakdown for each one. So like the whole synthesizer is like 400 lines. and Bithoven itself is less than 500 lines. And the nestration is the biggest part. And the reason it's the biggest part is because it's where I have like the programs for all of the instruments, and they just take a lot of code to write down all the numerical parameters. Also, this Bithoven part, inside of those 440 lines, that includes like the database of chord progressions and the database of parts and stuff like that. So what I'll emphasize is that this is a really small amount of code, and so I hope that makes it more explanatory for what kinds of for this sort of set of music. Now, something that's kind of neat about the nestrations is that by varying pieces of the nestration, such as what tempos you're allowed to use, what scales you're allowed to use, you can kind of create some emotional categories of music. So when I'm going to click this all button, it's just going to pick things, it's just going to pick a number totally at random. And it's probably not going to sound good. So notice that it didn't pick any drums, and it looks like there's like a warbliness, like some sort of weird vibrato in some of the pulses. So you can definitely see that there's some structure there, but I don't think it sounds very good, that one. But if I just decrease the number of scales that I can choose from, and I call this classic, it's going to sound a lot different. If it doesn't, I think there's something weird with the microphone, making it so that it doesn't, so that the speaker port is crashing. So I apologize. Let's go all the way to the end now. All right. So the only difference between this and the all one is just we've removed some of the options, but there's still a huge number of options. And we can do stuff like saying only use like a minor chord. Sorry, yeah, like a minor scale. It's going to sound sad. So you can imagine, you're walking through the dark castle in your NES game, right? Now, something that's kind of fun is I can click these blue things and it'll pop up and ask me for a string, and we'll turn that string into a song. So I'm going to say, Nara is really fun, but what about those deer? Okay? Naturally, it crashed. That was not as exciting. Sorry. Yeah. Yeah, really, there's like some global state there. All right, so we'll put that in. Okay, so that's that. So that string, we just turn it into a number. Now, if I pick a different thing, so I can sort of take the same numbers and see what they look like in different with different parameters, and obviously it's crashing. So I think I should end. If you're interested, I can show you these things later. Happy to answer any questions. Thanks.
Of course, we'll also hear more tonight. Right?
Yeah, so there's tonight there'll be a sample, a medley, but I actually don't know what it's going to sound like. I've just sort of, all I've done is I've chosen the parameters for the medley. Yeah.
I got it right, you were inspired by the Beatles, which can be heard from time to time. And what about Bithoven himself?
Yeah. So the reason the Beethoven influence comes from strict reliance on the chord progression. So Beethoven, he's sort of one of the founders of. See, I don't actually know anything about music, so it's hard for me to remember. But I was reading on Wikipedia about music theory, because that's where I learned everything. And I can't remember what the right phrase is. I think it's. I'm drawing a blank. But anyways, that's really where the chamber orchestra part of it. So everything is always 4-part harmonies, and so it's sort of deliberately classical sounding in that way by controlling the instruments. Because if you can do any music whatsoever, it's just too much for someone as weak-minded as I am to have that much freedom and options. So by drastically restricting the options, that's really where it's at all plausibly sounding. Yeah.
So you're supporting different scales like major and minor and that kind of stuff?
Sure.
And then do you have different sets of like chord progressions That's because those different scales, different chord progressions sound good in those different scales.
Correct. Yeah. So in the real world of music, different chord progressions are associated with different scales. So what I do is I have those totally separate, and so I think though that it makes it. I think it's still reasonable sounding when I combine things that are supposed to be with the major scales and put those with the minor ones, or with the or with the I don't know, like there's this one called the Arabic scale, so that's one. So taking the Arabic scale and using like the pop punk chord progression surprisingly sounds pretty neat. Maybe not as good, but it sounds neat. Yeah.
So is your numerical encoding tied to your database of chord progressions? So if you change the database of chord progressions, would the same number be encoded to different?
Yeah. So the question is, the number encoding, how is it related to the various databases inside? And so it's totally related. So every single number, because it's a bijection, it decodes to something. And so if you increase the set of things, if you increase the set of options at any point, everything else is going to move around. So yeah. So one thing that I should mention is that if you put a cap on the length of the songs, then there's a finite number of songs, because there's only so much variability within a single measure. So you can kind of think of it as there is a finite number of measures that Bithoven can produce, and then by stringing those together in longer sequences, then that's how you get an infinite number of them. But yeah, if you increase the number of chord progressions, there would be more measures. Yeah.
Why didn't you use MIDI?
Sorry?
Why didn't you use MIDI?
MIDI.
Sorry?
MIDI.
Oh, MIDI. Oh, why didn't I use MIDI? Ah, okay. So yeah, so so earlier in the project I implemented a MIDI decoder for the synthesizer, but I found that MIDI is like as a tracking format, it's too sophisticated for me, because it keeps track of things like when exactly does the key go down, and what was the strength of the key press and things like that, which are not relevant for the instruments that I have available. So basically it was burdensome. Now in terms of why might I not have generated MIDI as opposed to directly synthesizing? So both it is just a fun technical challenge to synthesize real time. So all this music was, real time generated from a slow language like Racket. So that's kind of a fun challenge. But I actually do generate MIDI, and I have, and because every Bithoven on the side, if I look in the current directory of this, there's going to be a PDF for the Lily Pond engraving of all the songs that we just heard. And so from Lily Pond, you also get the MIDI.
One more thing.
Yeah?
So there's been some work on using visual hashes in password dialogues to allow you to quickly use your visual memory to recognize whether you've entered a password correctly. Have you thought about using this to provide accessibility for visually impaired people in similar settings? Because it seems like you could just hash a password and turn it into a song.
That's cute. So I have not thought of that. That does sound like a fun thing. I wonder how. So because of the fairness, things that are locally different in terms of words are going to have quite big differences in what the song sounds like. So I would suspect that this would be a good thing for that visual hashing, because it means that if you're just one letter off, you're going to hear something that's really different. However, I think that there's too much. We're just speculating here, but I think that it's too hard to tell the difference between, was that an accented note in the third measure, or was that not an accented note in the third measure? Because there's definitely going to be those kinds of collisions at longer passwords. So if you make a big mistake in your password, it's feasible to me that you'll get a song that is reasonably close. But then again, no passwords are likely to be like hundreds of characters long, right? Because it takes the gaps between songs that sound the same are in the millions and millions with this thing. So yeah, that's a cute idea. Maybe I'll look into that.
You have to make it shorter, right? But the music, about every few seconds.
Yeah.
Otherwise, it's like the thing of an image, you can just look at it and it takes a moment.
Yeah, most of these songs, so in general, because I'm trying to generate retro music that is intended to be looped, even the longest song that it will generate is probably like 40 seconds long. But yeah, that is a little bit long to listen to. Did I type in the right password? But it's, I feel like it's a, we're within spitting different distance of getting something like 2 or 3 seconds long.
The rest will have to take offline. Thank you, Jim.
Very good. Thank you so much.